So if you have like you have a two element subset and R is a module over itself, say AB, then it's got to be linearly independent because A times B plus negative B times A is zero, right? So that's kind of the point of this. This one's, I think, pretty straightforward. A lot of you got this one. This one is, so if you have a free module of rank one, then that's essentially F is isomorphic to R as an R module. And from the previous, the R submodules are precisely ideals. And if we remember what a PID is, that means all the ideals are principal, right? So that means all the submodules are principal. All you have to do is show that they're actually free. So an ideal generated by a single element is free, and that's true as long as it's an integral domain, right? So that was essentially the gist of this. I felt really sorry for you all on 3A because I don't think anybody really, some of you actually did a good job, you in particular did, you almost wove it together, right? But here's the quickest way to do this, and this is gonna make you angry. Let R be commuted with identity, show that every R module is projected if and only if every R module is injected. I'll do one direction of this, and I think that from there you will see what's going on there. If you have, suppose every R module is projective. So you all, almost everybody started with like the definition of like an injective module in the diagram. Let's do it this way. Let I be any R module. And consider the short exact sequence. 0, I, B, C, 0. Right? Any exact sequence you like with I leading. C is projective by assumption. So sequence splits. Right? And so I is injective. Because what we proved is for every short exact sequence beginning with I, it splits. Right? So you use the fact that this is projective, it makes this split, which automatically makes this split, so you're good to go. And now you see how to do the other direction, right? It's just reverse the roles, projective and injective. All right. So almost everybody thought of this in terms of the definition, and it broke my little heart. There were 3 tears for me, so close. And what you did was you did the definition on 2 ends of the exact sequence, and I was sitting there cheering for it. Come on, stick it together. And you almost did. But anyway, it was pretty close. This one right here is number B. So you have 0 to U to W to V, short exact sequence. Now these are linear transformations, right? And so in particular, these are vector spaces. So this sequence splits because B is free, so it's projective. And when it's split, W is the right sum of the ends, right? And that's how you count the dimension, because the dimension of the middle has to be the dimensions of the sums of these two, because it splits. And this one is similar because you actually do need finite dimensional here, but you now have W is the sum of the dimensions here, right? And W is also the so the dimension of W is the dimension of the kernel of G plus the image of G. The image of G is the same thing as the dimension of V, and you deduce that basically what you deduce is the image of this, the dimension of this is the same thing as the dimension of U. It's a subspace of this thing of exactly the same dimension, and since it's a finite dimensional space, they have to be equal, right? So that's broad strokes. See if you can figure that out. Okay, any questions? Okay. Yes.
So you were saying that because they have the same dimension, that they have to be the same. So
well, and you also know something else. You know 2 things actually. You know that the image of F is contained in the kernel of V. Sure. That was encoded in the fact that I said that it's complex, right? And so what you have is you have the image of F is contained in the kernel V. You can use that other yang that I was talking about to deduce that the dimensions are equal, right? So this is contained in that and the dimensions are equal. Since it's finite dimensional, they have to be. Yeah, so you definitely actually need the finite dimensional business for that. Okay. Okay, any other questions? I'm gonna, let me patch that in, business from last time. So, we have, 0. What is this? This was a G hat. And that hat is split exact. For all our modules. So what we have last time is, this gives right out of the bat. See. Okay, so right out of the gates, we know that, right, from some previous theorem. Right? So really the only thing that we have to worry about is F is 1-to-1 and sequence splits. That's what's missing from this. We have to make sure we're patched together. Okay, so let's take in this sequence here. Take D equals A. And so what we have here is 0 into home R CD, home R BD, home R AD is, oops, and these are all A's now. This animal is splitting back. So, and let's see, we'll call this, this is F bar, and it's got a splitting K bar that goes back here. Okay, so let's take my favorite element of home RAA, the identity A. And let's just do K bar F to it. The fact that this is a splitting, of course, means that when you do K bar to F bar, you get the identity. So it should take the identity of A to the identity. But what this is this is F bar of 1A K, which is the same thing as KF 1A. And that gives you your splitting back here, because it tells you two things at once. It tells you, since the composition is the identity, it tells you that F is 1-to-1, so you get that. And it's the splitting as well. So any questions on that? Any questions?
So, like from before, is that how the functions always define that it like switches it for the contrarian one? Okay.
Yeah, and contrarian, that's right. Yes.
If you have the composition of two functions and they equal the identity, then inner one, like the first one you would do is one to one, and the second one you do is onto.
That is correct. Yeah, that's always correct. Okay, others.
If you have instead, like when you have a split exact sequence, you can run the arrows in reverse if you just change which ones are the splitting maps and which ones are the like actual maps.
Yeah, that's in a certain sense, that's right, because what it means to be split exact is the third condition that we had is it was isomorphic to that sequence.
Right.
We had A and C and A some C in the middle. And so that's essentially what a split exact sequence is you can actually run it in the other direction. Okay, I am going to give you, let's see. Theorem, I'm going to give you these two dual theorems. Actually, here. Well, actually, I'll go ahead and theorem like this. Okay, so these are two theorems kind of in tandem. Another pair of dual theorems. Theorem 12.74. The following conditions on the R module P are equivalent. So let P be an R module. Following are equivalent. And kind of do this parallel here. Theorem 12.7.5. Let I be an R module. The following are equivalent. Okay. A. P is projective. Dual motion, sort of. I is injective. B. If B from B that C is onto then B bar that goes from home RPB to home RBC is onto. The dual one is if from A, B is 1 to 1, then the induced tornado from home R BI to home R AI is onto good. And finally, and this sort of answers the question sort of about short exact sequence. If if 0 A, B, C, 0. First map pitchfork, second map phi is a short exact sequence. And so is 0 home R EA into home R EB into home R EC. And these are the induced maps P bar. And got an analogous one here. If say tornado and Ada is a short exact sequence, then so is the induced 0 into home CI, home BI, A. And this A bar. Okay. Any questions on it? So you can see, I hope, that this is kind of this dual motion kind of thing. That is to say, there's kind of a mirror image of the projective theorem and the injective theorem. This. Okay, so this will probably help you on your homework. Yeah, I should do the injective version on the homework, so let's take it. Right. Sounds like fun, right?
For being injective, so that one, like the contrary switches from one to one.
Yeah, that's right. That's right. Yeah, because notice that here the projective, so the variable is the second thing because you've got the projective constant first variable, and here the variables in the first order because the injectives in the second. Okay. Okay, so let's prove this. Really cool result. So projective proof. Okay, so P is projective. We want to, this is actually too hard for proof to do. So we're going to assume that P is projective, and we're going to show that if you have an onto map, then the home is onto. Well, so P is projected. And you have B from B to C is onto. Any ideas on how we're going to get that the home thing is onto? A lot of this stuff is couched in terms of exact sequences, right? All I've got here is just this little phi that goes from B to C. But I can turn this into an exact sequence. Right? Because with this being onto, I've got this chunk of it. And how can I complete this? Right. So what's the easiest lazy man thing that I can do here?
B.
Well, so I want it to be exact though.
Oh.
I mean, you're right, that is the easiest, lazy method we're gonna do, but I also wanna make it exact. So whatever this is, I need the image of this to be the kernel of this. Let me show you what a big fat cheater I am. How about kernel of this? Right, and just do the inclusion, right? And since this is an inclusion, this is 1-to-1, so now I've got to short that sequence, right? Like, okay, so far. So this gives, so in particular, how does this help?
Mhm.
Isn't there a splitting from B to kernel of phi?
Not necessarily.
You can
Right.
take. Like, the theorem where it's like, if that one is exact, it can only. Over, and then replace.
Well, so I put this terms of exact sequence, maybe perhaps I shouldn't have. So I can sort of build this exact sequence, but let's do this. Let's look at the definition. There, that's a better way to do it, I guess. So this is B, it's on to, so I've got my diagram. Yeah. Right, so I'll ignore this. I think this is a better strategy now that I think about it. So suppose I have this diagram here, right? Since P is projective, there exists H from P to B such that when I do H, then I do phi, it's the same thing as doing F, right? That's the definition. Okay. So how does that help here? Okay, good. So now this actually, if I read this and interpret it carefully, this gives me what I need because let's say F be in home R P C, which is exactly the setup of this diagram, right? That's what I mean when I've got this F here, is it's a homomorphism for B to C. Then there exists H in home R P B such that when I do H, this is equal to F. But by definition, this is phi bar H. Right, this is what covariant Hom induces. Phi bar H is this. Therefore, F is in image of phi bar. So phi bar is on to. Everybody cool with that? Okay, looks like we've conquered that much. So how about this is A to B. How about B to C? Actually, we've already done the heavy lifting. In fact, B is exactly what we need to make the exact sequence. Here's what I mean. If 0 A to B to C 0 is exact, then so is 0 to home R PA, home R PB, home R PC. And this is induced by the various Greek functions. Right, so we've got that automatically from that previous theorem. We only need P bar onto, but is guaranteed by assumption in B. Right, because if that phi bar is onto, which was here, then the induced is onto. And so if this thing happens to be onto, then this allows you to complete the sequence. And so it's exact. Everybody okay with that? Okay, so let's see if we can come full circle and go C implies A. So in this case, any short exact sequence leads to a short exact sequence in home. And I bet the last part's going to be the important part. We need to show that P is projective. So suppose we have the diagram B, C, 0. I'll call this G, E, and I'll call this alpha. Of course, our goal is to find some function that goes from P, some homomorphism that goes from P to Z that makes the diagram. Right, and well, let's see here. I guess we want, this is where I want the short exact sequence, I think, because we have a short exact sequence B, C, 0, cur G, and this is inclusion. Right. And what we know from part C is given this, then we have the short exact sequence. 0, home, P, cur G, home, R, PB, home, R, PC, 0. This is induced by G, this is induced by inclusion. So in particular, G bar is onto, right? Right? And that's, I think that is going to help us here. So notice that alpha is in home R PC. Right? And so G bar is onto, alpha is in home R PC. So there exists H in home R PB such that G bar of H is equal to alpha by the ontoness of that home sequence. And this, by definition, is GH. So there's your H here. It's an element of home R PB, so it's a homomorphism that goes from P to B. And when you do H and the G, you get alpha. So P is projective. Any questions on that? Alright. Go there. Okay, I'm gonna give you, this last one, and I'll discuss this briefly. Here, 12.7.6. Let A, B, AI, BJ, be R notches. A, any ideas? What this, I mean, what's on your wish list? What do you hope this is?
The product of the hops.
So, whoops, J,
It's a gym this mirror.
home, R. That is, if you look at the homomorphisms from A into the direct product, it's the direct product of the separate homomorphisms. Okay, how about this? How about this? What do you hope for here?
Direct on the outside.
Certain do, but that's not what you get. Exactly the direct product. So the sum pulls out into a product in the first quarter, right? Which is that's a little bit weird. Uh, so here's kind of a question for you. Can you give an example where well, so by the way, how would we prove such a thing? Maybe I should go through this a little bit here. So let's do this kind of a sketch. Let's kind of, I think it's kind of a good idea for us to kind of work together and think about how these maps should work. So let's try to go from, this is weird, right? From home R, A, the direct product of BJ, into the direct product of the separate homes. Okay, so let me kind of think about this before I do this. So my input my input is going to be, and this, I want to kind of talk through this a little bit because I think it kind of illustrates sort of that other aspect of the direct product. So my input is something like this, is F from A into the direct product. And somehow I'm going to associate with this a net or a generalized sequence of a bunch of homomorphisms from A to Bj separately. So I want to turn this F nice and neat into sort of this generalized sequence of homes, and each homomorphism, instead of, so F goes from A to the direct product, somehow I need to get F and break it down into its little pieces. So for every J in that entry there, I need a homomorphism that goes from A just to Bj by itself. Any idea how you might do that?
And you send it to the, uh, you send it to F of BI,
Sort of,
like restricted to that specific
Right.
index.
because, and this is one of the important things, the direct product was not just that thing. It's that thing equipped with those projection maps onto each bit, right? So when you have the direct product of CI, this is, of course, all these things. Right. And we know how to add these things. We know how to multiply by a scale, right? But also, for all I and I, there is pi sub I from the direct product for all, let's call it J and I, so I don't confuse this here. This projection map that takes the sequence and it reads through and barfs out the J coordinate. It's projection on the J coordinate. And that's what we're going to do here. My input is a function that goes from A into the direct product. And now I'm going to push on using that projection, right? So how do I get from A to Bj? A goes to the direct product of Bj. That was the first one. And then to Bj by projection. So this is the sequence I want. F so given any F, take that F and compose it, do F and then compose it with this, and this gives you a map from A to Bj, each one of these things. It's pretty easy to verify that this is an R-module homomorphism, and then it's from. See if see if you can verify this one. This one's a little bit more fun. Let me also point out, right. Notice that, let me also point this out. Pretty much anything else that you could try to think of with this is sort of not true. So Yes,
What if you have the direct sum in the right coordinate?
what's that?
Like instead of,
That doesn't work well either,
okay,
right? Can anybody think of a counterexample? Or the home of the direct, this is, it's not an easy counterexample. This. Let me give you, an example. Let me start with the following bidding group. So this is just the direct product, if you will. Right, okay. Let me also point out that there are lots of elements in here of finite order, right? 1, 0, 0, 0 forever is a finite order, right? In fact, any element, notice this contains the direct sum of that, right? The direct sum. Any element of the direct sum is a finite order because it has in an infinite string of zeros. And the largest order element is less than or equal to whatever the exponent is on the last non-zero entry, right? But there are also elements in here of infinite order, right? The element 1, 1, 1, 1, 1, 1, 1 forever is of infinite order as an abelian group because when you add it to itself twice, you get a 0 in the first coordinate, but it's not. So add it to itself 4 times, you get 0 in the first 2 coordinates, and you go on forever, right? So this has elements of both finite and infinite order. Agreed? Let T equal the set of G and G such that the order of G is finite. Yes.
With regard to that element that you're saying, the infinite string of ones in your G right there. If you write the limit of 2n times that element as that n goes to infinity, doesn't that limit go to 0?
Yeah, but it's still in a finite order.
Right, but the limit still converges.
I don't know what a limit is in this structure.
Oh shit.
Right, so that's an argument we'd have to have first. So these are the torsion elements. Just take everything in finite order. Notice if you add two things in finite order, it's still going to be a finite order, right? So this is actually a nice little subgroup, right? Notice this is strictly contained in G because as I pointed out, G does have elements of infinite order, right? Everybody agree with that?
Do we have T as a normal group?
It's an abelian group, so yeah.
Oh, okay.
Okay, so far. Okay.
Wait,
So-
how does every element?
Oh, right. We can figure that. Suppose, suppose I have a coset. And here I'm doing my group operation additive. Right? So N times G plus T equals 0 plus T. Right? Therefore, in G is in T. Right? So N times G is an element of finite order. Say it's order N. That means that M in G is actually the identity, which means that G was a finite order in the first place. And this is not true. Every non-identity, I should have said that, every non-identity has infinite order. Right, okay with that? Now, of course, G is the direct product of Z to N equals 1 to infinity. Now, if you look at home, Z, because this is groups of G, well, the direct product of Z to N to this has a non-trivial element, right? And I'll tell you what it is. It's a projection map that takes this, which takes G to G mod T, is non-zero. This is not the zero map, right? Because there are elements in here of infinite order. Everybody okay with that? On the other hand, the direct product of home Z of Z to N infinity G mod T is 0. And here's the reason. This is a finite group for every N. Everybody agree with that? This is a group that has every element has infinite order. So the only homomorphism that can go from here to here has to take everything to 0. So every possible home is 0. So in this example, you have a direct product of a bunch of zeros, which is 0, and over here you've got something that's not. So it doesn't pull out for the direct product in that sense. Any questions on that? Yeah, that's kind of a fun example, but see if you can look this over and look at other examples, almost nothing work, and see if you can prove the part B of this.